I've had, I think, quite positive experiences with experimental physics, and I want to underline experimental. The two most important are LIGO and CERN, but I also did much more work on earthquakes, turbulence, and wildfires. So those are the earthquakes, turbulence, wildfires are things that I've worked most on that overlapped with particularly geological and people work on turbulence. Wildfires is not so much a physics topic, but physicists have dabbled in it. So, but LIGO and CERN are the ones that are most relevant here, I think. And I had very, very remote involvement with these two, but it was a good experience. So in LIGO, the engineers who were building the experiments took my introductory robust control course. And that is about loop at a time design. And I'll mention this, that can be very dangerous. And so now one of the things that robust control can do is you can use just the analysis theory and not use any of the fancy synthesis machinery. And and it can tell you whether or not you have a bad design. So you do your best, and then you can analyze whether it's not good enough. Um, and but they turned out not to need any advanced courses, which was really a big disappointment for me. I was hoping I had all this great new theory, and they're going to use stuff from the '80s, and I was I wasn't too sad, but what they did was amazing. I mean, these two, both theoretically and experimentally, these are examples of just spectacular physics, and so I was very impressed with that. CERN was even more remote, which was they ended up building the fastest network so far in the world just to send their data around. And it was simply too fast for all the standard internet protocols. And so we tried ours, which I really mean Stephen Lowe was the leader on this, and I helped him with the math. And this was the first large scale deployment of our new protocols. And what was fun about it was the CERN people went to the internet meetings where they have these world speed records, and they broke the world speed record in some annual competition, but not really much to do with experimental physics per se. But good experience. And this was the theory that the LIGO students used. So I used this book, which was written in the '80s, which really tries to take the theories of robust control and redo classical control, which the hero of that is Bode, but there are many others, and upgrade it. And the little theorem on the right, or the little formula on the right, is what we call Bode's integral formula. And so what we did in this book was just update that a little bit and show a bunch of examples where it was relevant and so on. So if you wanted to do loop at a time control design, or if you just had a single loop problem, this was fine. Um, but loop at a time can be dangerous, and I'll try to just say a little bit more about that. But I want to talk about what I mean by architecture here. And so I'm kind of using it in overloaded terms because um, when you have layers and levels, which I'll describe, you end up having architecture everywhere. And so it's a kind of an overloaded term here. But what I want to do here is distinguish it, and I guess you probably can't see my forward, but from emergence. Um, and so architecture is a kind of complexity, but it's not just different than emergence. It's the opposite of emergence in a way we can make mathematically precise. So the new architectures, what you need to do is understand what this whole kind of diagram is. Um, and so if you were interested, you could also use this to really finally nail down what emergence really is, which is kind of voodoo now. Um, I'm not sure anybody cares because the people who are into emergence don't really want rigor. So who cares, right? So that I'm not going to try to talk about that today. I'm just going to put this in context. Okay. So there's sort of two dimensions, but there's three corners of complexity. There's simple, and then there's these three kinds of complexity. And I'm going to start out with this, which is um, uh, sort of the boring simple thing. So that would be a pendulum. Okay, and what are the laws? Well, you need to know what gravity is, you know, dynamics, you need to understand conservation of energy and so on. Very simple. And you can build clocks out of this. Okay. Um, so that's the simple corner. Okay. So what would architecture be? If this is a simple building block, what does architecture look like? Well, it turns out there's oscillations everywhere. Okay. You can see a list of these oscillations. And these are not some kind of emergent phenomena. These are, you design a system to have these oscillations. So if you're going to, breathe, you've evolved a system to breathe. You've evolved a system to beat your heart. Um, but you might also do a lot of other things like wheels, right? Wheels were designed to rotate. Okay. So this is what I mean by architecture in the context of oscillations. And then this has very minimal architecture. So this would just be, like a ratchet and a pendulum, and you could use this for a clock. Now both sides are useful, okay? But what you want is you want robust behavior, and you do that with complex mechanisms. So you have all these systems that can be quite complex. Um, certainly a very high-end vehicle now, like a new automobile, will be very complex. Um, but you want it to have very robust and fairly simple behavior. And that's the problem. So what is emergence? This is not emergence, okay? It's the opposite. So what is emergence? And maybe this architecture stuff kind of boring, because if it works, you never even know it's there. So right now, the amount of technology that's getting these slides to you is enormous, and you don't have to know anything about it. You just have to know how to use it, and with a simple user interface. Okay, so let's go back to our starting point and say, what is emergence? So what's the simplest thing we can do with this to get something that we might call emergent? Okay. So what you do is you can connect this sliding pendulum to a mass. So you have a mass here, and you have these simple equations. That's very simple. And what you see is you get this wildly chaotic behavior. Okay. So we can go back and do that over again, and you get this wild. So it's not simple like this down here at the bottom. So that's chaotic. Okay. So we found chaos, and that's emergence. Okay, wow. Okay, that's great. And so it's all over the place too. Okay, um, so the way you approach this is things like coarse graining. You have self-similarity. You have scale-free networks. You have self-organized criticality. You have the edge of chaos, the edge of all sorts of things. Okay, so very popular subject. Um, so what's architecture? Well, if emergence you get from coarse graining, then architecture you get from fine sculpting or fine tuning or lots of other terms you could have here. And they're really the opposite. Okay. And so we're going to want to be in the architecture corner. Now we may want to study emergent phenomena with the machinery we build in the lower right hand corner. But if you're an experimentalist, you're in the lower right hand corner. So we have this simple picture. So what's an example of this that would be more like architecture? Well, it would be balancing the pendulum. It doesn't fall over. Now, this is not simple like the original case because it has a very sophisticated control system, but it's relatively robust. And so it's the same model there, but you have this, in this case, a human. It's probably easier. It's easy to do this demo with humans, whereas if I was there, I would show you this demo, but if I had to bring a robot to do this, it would be cumbersome. So I'm not doing it because robots can't do it. I'm doing it because it's just simpler to do it with humans. And so what you want to do is, what is the theory that tells you about what's going on in the lower right-hand corner that is much far beyond what's in the upper left-hand corner? Okay. And so what's the theory of robust architecture? What's a baby version of that? Okay. So, and where is architecture? Well, architecture is everything that's evolved since bacteria. So it's our biosystems, ecosystems, technology, society, and it creates all entirely new laws that have nothing to do with physics. But it also creates new fragilities that are often catastrophic. And so you can say, well, whatever happened before bacteria is physics and its emergence. Okay. So you have all these things like self-similar, scale-free, self-organized, and so on. And architecture is self-dissimilar. So if you take your body and zoom in at the small scale, you don't see little copies of your body. You see cells. Or if you look inside your car, you don't see little cars. You see something very different. So it's scale rich. It's mostly evolution. I wish there was intelligent design. There's not enough intelligent design. Um, Autocatalysis is really crucial. And if you want to call this emergence, then it's extremely strong form. Okay, so these are really opposites. And we could say, oh, the whole is greater than the sum of the parts. That's a useless platitude, right? So, um, but also there's this corner, and architecture makes this corner much worse. Okay, so that's one of the things. So we got disasters everywhere. Okay, yeah, this is a picture from within the last year. I mean, if you are an expert, you have no idea where this. This could be like 5 places on the planet, right? So could this, right? This happens to be Los Angeles. I don't know where this is. This is another one, right? So I think one of these is Ukraine, one of them is Gaza, and one of them is Los Angeles. But you have disasters all over the place. So there's all sorts of fragilities like microbes, cancer, brains. One of the ones I'm particularly interested in now is patriarchy. But technology has a lot of fragilities. Okay, so can we use this little simple toy example to start understanding what those fragilities are like? And so there's sort of these three corners of complexity in some sense. There's the chaos, there's the robust and stable, and then there's the crash up here, right? And so this crash is just a modification of this, good working robust system. So so the idea would be, I mean, again, this is like another trivial example, but the idea would be um, if you had a large asteroid circling the sun, okay, that's pretty simple. Um, if you have two large asteroids colliding, you're going to get emergent phenomena. You're going to get pieces flying all over the place, and you're not going to have a simple picture. Okay. Now, architecture, if you took technology and deflected a large asteroid that would otherwise hit the Earth, that's architecture. Very different. Okay. And then a large asteroid hitting Earth can be a disaster. Okay. So, and that would also be emergence, right? Um, so disasters can be emergent. Um, Now, here's another thing which I'm going to talk a little bit about is power laws. Power laws can emerge from very many simple processes. But the ones that you actually see in the literature are usually just errors. They're not really power laws. Okay, so it turns out power laws, the simple version is that they're just a central limit theorem. So you might imagine the central limit theorem gives you normal distributions, but in fact, the generic thing it gives you is power laws or what's called stable laws. And Gaussians are a very weird special case. Now they happen all over because of the way we study the world. But mathematically, you would think of as the Gaussian, no, if you would not think of that as normal, you would think of power laws as normal. So it also turns out that the robustness and diversity that we have in our big complex networks necessitate power laws that are beyond the central limit theorem. Okay. And then disaster statistics have power laws that are due to architecture and are not emergent at all. And so this is a source of enormous confusion. And even within engineering, it has been a source of confusion, but mostly it's cleared up there. And it's still, I think, a problem in physics. So what goes on over here? What are the laws of this right side? Okay. And that's what I want to tell you a little about. Now, normally, if I was there, we would do live demos with an extended pointer. You're going to have to just kind of imagine this. But you can get one of these extendable pointers and play around with it. So it's a really easy example to do. Okay, so here's the story is there's a theorem that says if you make, sensible models of this, you can show that um, and think of this as just how much any kind of noise is amplified. So but the idea is that there's a theorem that says as you make the stick shorter, it gets more unstable and it gets harder. That's pretty simple. Okay. Um, so that's not too surprising. Okay. So, but here's the interesting part is If you make the stick long, so if you start here and make the stick longer, okay, which makes it more stable, but you don't change where you look. If you keep the same place here, um, then it's actually hardest by a lot. And you can try this yourself with an extendable pointer. And so what you have these universal laws, and that's what's in this book. And so the idea is that if you shorten this, it's hard, but if you look down, it's much harder. And you can quantify this, and then it fits the data perfectly. And the same universal law applies to all sorts of things. So I have power grid and airplanes and stuff here, but also glycolytic oscillations. It's a paper in Science. And it turns out this big mystery was, why does glycolysis oscillate? And we said it's an unavoidable side effect of this law, but you never see it in intact cells. You only see it in extracts. And the reason you don't see it in intact cells is because the cell makes sure you never get in the regime that it's going to oscillate. And so that was very controversial, but it obviously eventually got published. That was a miracle. But the idea is that there's this same, you do a mechanistic model of glycolysis, and then you apply this theorem, and you get exactly the same result, that you're going to have oscillations. And so, the power grid does this. A lot of things do this for the same sort of reason. And so what happens is, what you want to have is a theory where you have conserved quantities like energy and materials and small moieties, but also you want to have robustness, which isn't part of physics or chemistry. So fragility emerges in this direction, but architecture is for robustness. Okay. Now, because robustness is conserved, you can get yourself into a disaster this way. And by the way, these disasters can be as bad as anything that's emergent. Okay. But they're very different in how they arise. They are completely different. So again, this would be a large asteroid circling the sun, convergent, emergent here. But then if you really want to destroy things, you want to put atomic, bombs on the top of your missiles. So if you just flew the missiles, they'd make some, they'd land and crash and make some damage. But if you put a thermonuclear device in the tip, it's much worse than just that alone. And again, this is trivial, but the idea is that this kind of many missiles hitting the Earth is much worse than a bunch of asteroids hitting the Earth of the same size. Okay. So theoretical physics is mostly about emergence, but you people who build things, it's mostly about architecture. And that disconnect, I claim, is at the heart of a lot of the current lack of unification. It causes unnecessary fragmentation. I think quantum mechanics and gravity is the poster child for that. So if this is ever going to get fixed, it's going to be fixed by experimentalists just doing the theory instead of the theorists. And if anybody wants to talk about how to go about that, it's not easy. I'm not claiming this is easy, but if you only use theoretical physics and you don't use the understanding that you're going to get about what the experiments are doing and what measurement is doing, then you're going to have this weird mystical view of measurement that is completely unnecessary. So I want to talk a little bit about this idea of layers and levels, because that's the most important distinction to be made in architecture. And this is a picture that has both layers and levels in it, and it's really confusing. And it comes up in biology and engineering, but it really hits you in physics. And like I said, there may be unnecessary fragmentation by not thinking about, this is what a physics experiment looks like. This is what all biology and engineering looks like, but this is what a physics experiment looks like. And this is not what theory of physics looks like. And that's a mistake. So what I want to tell you about is what layers are. And I'm going to use a sort of toy example here. So what the difference between levels and layers is levels zoom and layers stack. And I have to explain that to you. But a confusion that comes up in some areas, and it happens in biology and engineering, but really badly in physics, is that the levels and layers have the same names. And that can be really confusing until you sort it out. Now, fortunately, actually, in most of biology, for example, they don't. And most of engineering, they don't. They have nothing to do with each other. I mean, they have something to do with each other, but they're not labeled the same. Okay. And so we're going to talk a little bit about this idea of what layers, levels, laws are. And I'm not going to, have time to do this justice. This is a, whole course at Caltech. But we wrote a book or wrote a paper recently, which is, and since you have the slides, you can go find this. And this is in the Control Systems magazine. So this is written for control engineers. But because many of you have good controls backgrounds, you'll have no trouble with this paper. It's very accessible. It's really easy. And it deliberately avoids arguably the most important topic in the subject currently, because that topic is gotten so much attention that it tends to be the tail that wags the dog. And I will spend the last part of the talk telling you about that. So, and here's another paper, which appeared in PNAS, and it basically tries to distill the essence of layered architectures using biking, and it's all high school math and experiments. And so the math is really easy. So this is a talk that I gave at San Diego, where I live now, actually. It turns out I'm retired now, and so I moved to La Jolla. But this has this talk, and it's complementary to this because it's very much oriented at brains and society and stuff that's made out of brains. Okay, so but let me go back to the 70s when some of this kind of got started. And so the idea is that here's layers: navigation, guidance, and control. So the idea is navigation is where am I and where do I want to go? Guidance is how do I get there? And control is how do I stay on the path despite disturbances? Okay, so this is a layered architecture, and it's the oldest sort of major case study in robust control. So this happened in the 70s. Okay, and this is what I was an undergrad at MIT, and this is what you learned was, sort of the aerospace stuff. And then I was also consulting for Honeywell, so I saw this from the side of the engineers. And so this stuff used modern control theory, I think, quite effectively. So Bellman, the names for Bellman, Pointryagin, Kalman were used in this part of the system. But at the time, in the 70s, this was done with classical control. And that would be like Boda, Nyquist, Nichols, those people. And this was a point of contention because the academics said, you guys are behind. You're using this old stuff when you should be using all this new stuff that you already do use in some places, but you don't use it for control. So the idea was modern control had come along in the 60s. And it was, Kalman, Rosenbrock, Athens, people like that. And the idea would be that should replace classical control. Okay. And the fact that it was not doing so was we called it the theory practice gap, and it was a problem that the engineers had because they weren't adopting the latest theory. And I was taught this. And then I also was spending, even as an undergrad, I was consulting for Honeywell, so I was seeing both sides of this. Okay. So what can go wrong? Well, here was the problem. Modern control really was this like Potemkin village, right? And so the idea would be if you use modern control, you would be robust. You didn't have to worry about this. I would say this was the world up until 1978. Okay. And I get this picture like a Potemkin village, right? So, okay. So as an undergrad, I actually did this work. It took a little while to publish, but this put a torpedo through this idea. And the idea was, the title was what everybody expected some paper to soon come out with. This is a conjecture. Everybody believed it. And so when I wrote this paper, shortest abstract in IEEE history, that this just isn't true. There are no margins for guarantee. There's no guarantees at all. So if you use this thinking you're going to get guaranteed robustness, you're kidding yourself. Um, so that kind of ended there. Um, but modern control was much more than LQG, right? There was loop at a time methods, which was kind of more classical, but there was a thing called Karaskoside, diagonal dominance, pole placement, all sorts of stuff. So what I did that same year is I wrote a paper that, so this first one was this was only the first one. So, but LIGO used loop at a time, right? And so what we said was all of these, this just said LQG was bad, but this paper said they're all bad. You can't use these. But the point is, you can't use these, and without augmenting it with robust control, you're going to make errors. But here's the weird thing is, you could still use all this stuff and you get lucky and get a robust design. You can check that it's robust, and then you're fine. But the problem is a lot of them didn't. But what was amazing about LIGO was they did use loop at a time, and they made it work. But they made it work because they were able to analyze it. So why are we still teaching LQG, right? Well, it's still a good introduction to state space and all sorts of things. So, but what we're going to do now is go beyond, and this is now robust plus this thing called system level synthesis, SLS, because it's not stochastic, but you have friends and foes. So you have teammates, you have adversaries. You don't care about energy, you care about norm bounded errors. You're not risk neutral, you're risk sensitive. This is the big one, the big new one. As we always assumed up until recently that we had fast, accurate hardware. So if you're flying an airplane, everything's speed of sound except your electronics is speed of light, and you don't have to worry about that. That's not true in biology. It's not true. It's not true in technology anymore because you build these big systems that span the globe, and all of a sudden, speed of light is not fast enough. And so, and not only things not centralized, we have localized, distributed, delayed, all over the place. Okay, and so we still have internal models. We used to have sparse actuation and sensing, and now you have sparse everything. And it's this sparse everything and the hardware limits that I want to, kind of focus on. And these are, so if you want to learn about this, of course, there's two courses at Caltech. I'm retired now, so somebody else has to teach these. But so this would be the introductory courses at graduate courses at Caltech. Okay. So I want to talk about this a little bit and what the consequences of this are. Okay, so there's lots of other examples I could use here. So every one of these is an example. Some of them are really serious, like cells and organisms. But then there's things like clothing, cooking, baking, Legos, and these are fun because you can teach a lot of the ideas using these examples, and everybody gets it, right? You can teach it to anybody, and so you could again teach this stuff in high school. So what can go wrong? Well, a lot, right? Okay, so fire is one thing that can really go wrong. And we had an example of that. Now, I fortunately moved out of the LA area in November, so I missed all of this. But I'd worked on this, decades ago, and I could lie to you and say I predicted that this was going to happen, but I was not. My prediction was off. My prediction was that it was going to be much worse than this, and it was going to be way sooner than this. So I was kind of looking at this worst case robust scenario and what was LA County going to look like under drought conditions with Santa Ana winds and so on. And I thought everything would burn. So not everything burned. So I was overly pessimistic about that. Okay. But did work on this. This is a paper that I was a co-author on in about just the history of fire. But this is a paper that I want to tell you a little bit about, which is a PNAS paper in 2007. And this is one of my main co-authors with Gene Carlson. And then these people up at the front were all experts on fires, and then physicists, and then me. Okay. So where did this start? This started with a science paper, 1998. Self-organized criticality. So I'm sure you've all heard of self-organized criticality. And so they said these forest fires have power laws, and they're an example of self-organized criticality. So there's 4 data sets, and these are binned data, and this is an example of what I call complexity science. So it's not really, they call it complexity science, but I use the word science, and I'll kind of explain that in a minute. But the idea is that these plots are completely bogus. Here's how you plot them correctly. Okay. And they're not exactly power laws, but they're high variance. So you look at this on a log plot. So they're not quite straight lines, but they're very high variance. Okay. And that's the SOC model. So the SOC model that they proposed is very strongly refuted by the data in their own paper. They just did the statistics wrong. But the way they did the statistics wrong was absolutely standard in statistical physics. So they were doing everything right. It's just that it was all wrong. And so because this is a log plot, these are order of magnitude errors, right? Huge errors. So we wrote this paper, and what we did is we said, okay, let's look at a bunch of different sources of data. So let's take the best data set available in the world for 90 years on Los Padres National Forest. So this is the most complete data set there's ever had on fires, just almost down to the trees burned. One of the best data sets available. Then the other thing we did was we built a simulator. And again, the simulator was just put together out of existing standard pieces, right? So there was people who had vegetation models or people who had, and the biggest thing was we used the same fire simulators that the firefighters used. So this is the really state of the art. And then we made up like a little toy model you could do with high school algebra. And I'm not going to tell you much about this model. It's just, you know, could we do something simpler than self-organized criticality that actually made some sense? And that's what we did for that. Okay, so I'm not going to. Okay, so here is three things. We're plotting the data in blue, the simulator of the same region, but with state-of-the-art simulation over 500 years. And then this is our toy little model. And they lie on top of each other. I mean, it looks like I photoshopped this, but this is real. Okay. And then I've plotted the SOC model, which again, this is unbelievably wrong, right? And so you have these two worlds, which is the self-organized critical wildfires, which hypothetically could exist. It just doesn't exist in reality. And then there's the real fires. And they're the opposite. And the reason they're the opposite is because a forest has a lot of architecture. It isn't just a sand pile. Okay. And if you put that architecture in, either through massive simulations or in simple models, you get the right answer. And so these are the four data sets that were in the science paper plotted correctly. And these are our simple models. And like there's two parameters. So this is not like overfitting. This is, a couple parameters, and it fits every one of them perfectly. And then the SOC model is like way off, right? And so so there is a law here, but it's absolutely not SOC. Okay. So in the SOC models, the low end small fires, okay, sorry. What about the data? Why does the data end here? Well, because they don't keep track of small fires. And then the highest cutoff is, why is there a cutoff here? Well, you can only burn the whole forest. Okay. So there's upper and lower bounds on the data, and that's what these tails are dominated by. Okay. So there may be a law here, but it's not a power law, and it's not self-organized criticality, because that's what SOC says it should be. Completely wrong. And this is, I hesitate to say that this is all of theoretical physics, but a lot of theoretical physics makes these mistakes. Okay, I'm gonna. So it looks like a hoax, right? It's so wrong. It looks like a bunch of literature majors decided, oh, we're going to pull a hoax on the scientists. But it's not a hoax. And in fact, these errors are mandatory. You don't get published in science if you don't make these errors. And so who knows what to call it, right? And even the original SOC paper was wrong. It said self-organized explanation of 1 over F noise. In their own data, it was really 1 over F squared noise, which didn't need a special explanation, right? And so never corrected. None of this stuff has ever been retracted. And it's gotten worse since, I think. So we wrote all these papers back in the, you can see the dates, 1999 through like 2009. Utter futility. Now, what's good is that the people who are experts on wildfires were totally on our side. The people who are experts on all of the actual applications, including LIGO and CERN, right? They were on our side. They were using all our stuff at this time. But the core theoretical physics community ignored this and keep going, right? And so I call this science, like it's zombie science, right? It's like zombies. So it's like it's not true, and it's useless, but it's contagious, and you can't kill it. It's like so I call that zombie science. Never retracted. None of the stuff was ever retracted. So okay, so so what I want to do is I want to talk about the latest thing, which is called system level synthesis. And how am I doing on time? Not too bad. Okay. If this was live, I would say ask questions while we're going, but it's kind of cumbersome in this, so I'll have questions at the end. So I'm going to kind of go through this quickly. There's tons of papers on this, and I will tell you the students whose current websites have all the latest in it, right? And so here's the idea is here's a control system. And because you people have controls backgrounds, I can just draw it. And I can say, look, you've got a plant you're trying to control. I'm not going to say what that is at this point. I'm just some generic plant. And you've got computers and you've got communication and you've got sensors and actuators. And everything is sparse and delayed and local. Everything. That's what a lot of the real world problems is. That's what the power grid looks like. That's what the internet looks like. That's what all of biology looks like. That's how your brain works. Everything. Okay. We in early applications of control theory, like aerospace and stuff, we didn't have this. Okay. And so what I'm going to try to do is talk about a control system where you've got, your usual control system. And so, but instead of that picture, you have this picture. So this is a controller, but the controller has a lot of structure. I'm going to kind of go through this quickly, but the idea is that what I do is I look at the closed loop system. So I have a disturbance into the state, and I have a error on my sensor. And so what I can do is I can look at the map from delta X and delta Y to X and U, and that's the closed loop. And so we'll call that phi. So here's the interesting thing is, in order to do this the way we're going to do it, is we're going to not design K. We're going to design the closed loop subject to constraints, and those constraints will ensure that there exists a K. But we're going to take a problem that is wildly non-convex in K, turn it into a complex a problem in phi, and then we can impose all of these constraints. And then once we've got a phi that satisfies all the constraints, one of those constraints is that there is a K that will do this. It's just a mess. But now you just solve for it and you pull out the K. This is the best idea I've seen in 50 years in control theory. So I'm going to take a really special case, okay, where the K is this yellow boxes, the red is the plant, and then the sensors and actuators are in green, okay. And I'm also going to assume that the sensing, the communication speed is fast, like twice as fast as, so the wires on the top are twice as fast as the other wires, okay. That's often the case. So you often have speed of light electronics, and they actually are faster, but they're not wildly faster. So in the power grid, for example, it's all electrical, but the actual dynamics of power transfer is slower than the dynamics of sending bits around. So here's what localizability is. I get a disturbance in my plant. That's my plant element down there. I get a disturbance there, and I get a state deviation. Okay. And after one time step, my computer up here knows about that disturbance. Okay. But also at the same time, it's propagated. So the next time it's gone 2 steps, and this has only gone 1 step. Okay, that's why it's twice as fast. So the disturbance is propagating through the plant, but it's also propagating through my computer network. So the 2 times the speed, so I'm starting to get ahead of it, right? And then now I'm ahead of it. And now I can take a coordinated action to stop it. Okay. And so it doesn't propagate anymore. So the next thing is 0. So it stops the propagation. Really simple idea. Okay. The question is, can you make this, scalable and everything? And so the idea is that now you have a system like this, and what you're going to do is zoom into a patch. So you zoom in, you've got a bunch of controllers, you've got a bunch of communications, you got sensors and actuators, you got the plant. So we're going to zoom into a plant. And so what we want to do is everything is localized, right? A computer only talks to its 2 neighbors. And so it's very, very localized. But we want 2 things. You want the control to be localized. You want the control to stop somewhere, even though, and you want the disturbance to stop. So 2 things. You want the disturbance to not propagate very far. So if you have a power outage in a neighborhood, you want it to just spread. You might spread it a little bit, but you don't want it to go very far. If you get an infection, you want to have it stay where you get the infection, whatever. Okay, so that's called localizability, and that's called, in this case, it's finite impulse response. It doesn't need to be. You can have exponential decays, but it's easier to visualize. So what you want to do is you want to be able to do sparse distributed unlocalized control with delay communication. So the idea is that all of these things have delays in them. And we're used to the delays in blue being so fast relative to delays in green, we don't have to do it decentralized. Okay. And so we're going to assume sensing is dense, but everything else is sparse for now. Okay. So now we get this open loop response. And we're going to look at that, right? So what we're going to do is we're going to spread this out so we turn this over, right? We're going to go back, we're going to twist this over and put it vertically on the left side. And then we're going to look what an impulse response looks like for a really big chain, no control, open loop. Okay. So the idea is that that's the picture we're going to draw. Okay. And I got to explain that. And what the idea is that this is kind of neutrally stable. And so you can see on the right, you can see the legend. And so space is going this way, and then time is going this way. So you have to have a 1-dimensional space in order to do this, right? So it's a chain, which is a very special case. And this is what open loop looks like. And this is really bad. This would be like everything burns. The whole power grid goes down. You get septic, you get sepsis, or, cancer takes over your body. These are all the bad things that can go on. So you can try and idealize control. So it's not implementable, but we can sort of look at it. So suppose everything is instantaneous, right? Dense everything everywhere, okay? And that's how we've been building control systems forever. And if you can do that, this is what the state looks like. It exponentially decays and it's localized. Now we had some work, over a decade ago that took a little baby step to this where we could take LQR and do it in a distributed way. I'm going to not talk about that. I'm going to talk about the latest thing. So now we're going to look at the impulse response, both in the state here, in the state. Okay, I'm not going to use the pointer. You see the state and the control both have an instant response. Okay. And that's what a centralized controller can do. And what you see is that it just has exponential decay everywhere. So what we'd like to do, we'd like to do something better than that, right? And so we're going to look at this and we're going to just draw this cartoon version of it, just so it's a little easier to see and move around. Okay. So what we want to do is this is global, dense, and instant. We don't want to do that. We want to have we don't want to have it to be not global, not dense, not instant. Okay. So what we're going to do is here is an alternative. So on the left is the state and control. On the right is the new design that I'm not yet telling you how to do, but this is what we want to do. Okay. And so the idea is that you're going to design these closed loops. So the idea is that what you do is you can put the constraints on those things you're looking at. And if you do that in the right way, you can guarantee that you have sparsity and locality, and you can get a K out of it. And that's the big theorem. Okay, so I'm not going to explain that. It's not hard. It's some of the easiest control theory I've ever worked on, and it's also the most profound. So we're going to zoom in, and what you see there is you see that you get the spark, and it quickly gets killed. But you do this with only local control and sparse control, right? So we're not actuating everything, right? So you design R, M, not K, and you do that in patches. Okay. So this is all designed just locally. So you design and implement locally, which is amazingly scalable. But then the result is everything is localized. Okay. And so again, I'm not going to tell you about this, but it's kind of it's a small miracle. The idea being that if you design M and R to be sparse and local, K is as well. So again, it's a big miracle. If you write the formulas out, K inherits the same structure as M and R has. Okay. I'm not going to go through that, and just because we don't have time. Okay. So that's what you do. So we're just going to again make this cartoon patches. Okay. And so the idea is that you want local, sparse, delayed, everything, and you get a localized state and you get a localized uh, control. Okay. And then you can also have sparsity in there by just saying there's parts of the control action that are zero, and I'm indicating zero by black. Okay. So instead of the left, which is global, dense, instantly, and memoryless, you get the thing on the right. So I'm gonna actually skip this part because I haven't told you kind of what the circuitry is, but again, the papers are very readable. So you can start with this, right? And this is what you want. Okay. And that's the controller. Okay. But not only what you want is everything to be sparse, delayed, and quantized. Okay. And there's all sorts of extensions. There's model predictive control. There's data driven. There's nonlinear. It's been extended to PDEs. It's been extended to co-design. I'm going to talk about co-design. And these are the people. So since you have these slides, you have their names. They're all my students from oldest to youngest. And the reason you can't find any of this by searching on my name is I don't co-author papers with my students. Just a kind of a policy. And I would say, oh, it's because I'm really a good guy or something. No, I'm just really lazy. I'm a co-author on the very first papers, but then all this elaboration of it, I move on. I want to do something else. And so, but these people are fabulous. So Matni's at Penn. Anish Sarma has just finished medical school and he's now doing residencies. Carmen's at Stanford. Lisa Lee is at Michigan, and Lauren is still at Caltech. So she's our latest. And they're, like I said, MPC, data driven, nonlinear, lots of AI, lots of machine learning, lots of large language models, all that kind of stuff. I'm not going to tell you about any of it. Okay, so the idea is that everything is sparse. So, and it's layered. And these are what I'm going to call layers are computing, communication, sense, actuation in the plant. Those are layers. Okay. But levels zoom. So what's the difference between layers and levels? Levels zoom. Okay. Now, of course, when I draw it like this, you see the layers right away. But of course, if you just zoom in on the parts, you just see a pile of parts, right? And so, but you can organize them on level zoom and layer stack. That's the difference. We have a box of junk. We open up and see all the junk. And that's levels. But if we look inside and say, hey, wait a second, this junk is organized into layers, that's what layers are. So layer stack, level zoom. That's this picture. So what you'd like to do is co-design everything. You'd like to design the whole system, put constraints on everything. What can just put constraints on what you can build, then what you want to do with the whole system, and then you want to have it all designed top to bottom. And I think that's what you want to do with your experiments, is do like what I call full stack design. So you want to minimize robust errors subject to all these sparsities and delays and everything. And then and you want to have sparsity and delay subject to robust errors. Okay. And the way you do this is you take little patches like we did before, but now it's not just in one dimensions, and everything is localized. And then you make sure that it all sticks together. Okay. So I think I got a cool example here. Okay, so we're not doing that. We're going to do. So here's a question: where do we want to put the actuators? So that's an example of we want to have that be a control design. So we want control design not to be just about controller, but where would I put the actuators? Because in a lot of situations like this is a real big design error. Okay. So what we're going to do is we're going to take this picture and we're going to look at distributed and sparse control, but we're going to decide where we're going to put the actuators. Okay. And so, so then the point is, where do you stick all this stuff, right? So we're going to look at power grid. So this is on the left is a well, it's actually a made up topology for a power grid. And at every node, there is this oscillator. And this is a basic simple model of frequency regulation in the power grid. Okay. And so you have these subsystems interacting with each other. So if you get a disturbance in one or the other, it can propagate, right? And so this is like 2016. So this is a while ago. This is 10 years ago. And this is this Nikolai Motny and Yuxiang Wang, who's also a student of mine. But he went off into industry, and so he's not as active in publishing anymore. Nick is very active and doing a lot with how does this work with AI. But this is old stuff, but it's still pretty interesting. Okay, so if you look at the right, each blue line is a wire, and each little circle is a node, and that node can, in general, would be either a generator or a consumer of electricity. Okay. So what we're going to do is we're going to look at what happens if you have, this is just a standard off-the-shelf model of a power grid. And so nothing special here. And we're just putting a control system in. And this is just open loop. This is what happens to a disturbance that's open loop. It's really bad. I mean, this is basically how a global blackout happens. It starts in one place and propagates. Okay, so this is how you get blackouts. So now, if you put actuators everywhere, right, and you put computers, you put everything everywhere, right? This is centralized control with dense actuation. Okay, prohibitively expensive, but this is what you'd like to do. So you keep getting hit by this disturbance and it just doesn't propagate. Okay. That's what you want. But this is too expensive. This is prohibitive. So, okay, let's just put the actuators at random. Okay, let's see what happens. And if you do that, it's not very good. Pretty poor performance. But it's cheap. So the question is, can we optimally design the actuators? And that's what calls co-design. And so what this SLS theory lets you do is lets you do this. And so what happens if you do co-design of the 261? It's good performance at moderate cost. So it's almost as good as if you had dense everything, which is prohibitive. Okay. And this is also you can also design to be as bad as possible. So you can make it really terrible. Okay, so that would be really stupid. But this is still an optimal controller with the actuators in really bad places. So here's kind of a picture. Let me see if I can explain this. On the x-axis is the number of actuators. And on the y-axis is how fragile it is. And you can see open loop is pretty fragile over here. Over here is open loop. It's pretty fragile. Um, and then the perfection here is this dense thing. And of course, you'd like to be ideally in that corner. You'd like to be super robust and not use any actuators. So the extreme on the far lower right is what happens if you just have dense actuators. But what you want is that sweet spot. So you can't quite be ideal, but you can be damn close. So you're nearly as good as the as this impossible ideal dense here in the corner. Okay. And so what this whole framework lets you do is lets you systematically do this kind of um, layered design in an integrated way. Okay. And so then the question is, now you can ask, what are the fundamental limits? How close can we get to that ideal? And so what you want to have is a theoretical framework that lets you do that. And again, this is what I believe you're going to want to do as you go forward in ever more advanced experiments in physics. But again, I think it would benefit the theory to use this mathematics to describe the theory as well. And this overcomes this horrible combinatorial design space, which is sort of, so it's like 2 to the number of possible cyber alternatives. That means all the sensors, actuators, communication, computing, everything, hopeless. And this does it very efficiently. And so that's done with this co-design. Okay. And how much does this cost? Okay. So in red this is just kind of a generic control system. So you can see the number of states on the bottom from like 1 up to 100,000, and the time it would take to run on, depending on the kind of computer you have. Okay, um, so there's the centralized design, and that's expensive to compute. Then there is the localized design, which I talked about. But that's the curve that you would get if you did the computation serially on the same computer. So you have one computer and you do all the computations. Note that you get a big improvement over the centralized as you get to larger number of states. So that gap is substantial. However, if you use all the system level synthesis, you can actually do the design localized, and that's this line on the bottom. So not only are you getting performance that's very close to centralized, you're doing it with much less hardware, and you're also able to compute it much more cheaply. Because what you do is you use the same computers to implement as you do the ones that are implementing the controller. You can use them to design the controller as well, because the computation to do the design is really cheap. And so, like I said, this is, maybe oh, definitely. This is the most exciting thing for me in 50 years in control theory. And so eager to get this out and used by more people. And I think I'd love to help you do this, but I think it's a thing you want to have out there in experimental physics. And once you're down this path, you're going to find out that theoretical physics is inadequate, and you're going to want to fix that as well. Okay, so here's the problem, which I'm just going to finish with, which is that's what experimental physics looks like. It's got levels and layers, but it turns out they're the same, which is really weird. A very special case. And the idea is that what you want, and so this is experimental physics full stack. So this is what you have to do. So somewhere down there, there's lossless, which is, somewhere down there, it's all quantum mechanics. And somewhere up here is a digital computer, and you want to be able to, connect the two, right? But sustainability of anything is full stack, right? You want to make systems that are sustainable and not wasteful. Then you have to use all of this theory, I think. And there's all sorts of passive mechanisms. Okay, so we did a little toy version of a redo of a little bit of physics, which is just the statistical physics part. And that's a couple of papers that you could look at if you wanted to. And so this is, this is, 2011, this is, I don't know, 2019. this is definitely a hobby. And so just playing around with this. But the idea is that we said, what if you had control theory? How would you do statistical physics differently, in the 1800s? What if Boltzmann had known this stuff? What would he have done? And we claim you end up with a statistical physics that's quite superior to what is standard taught. But also what ends up happening is you have a theory of measurement. So when quantum mechanics came along in this counterfactual world, there would not be a weird story about measurement. Measurement would have just been the same as it was classically. Totally makes sense. No big deal. You don't have to worry about consciousness or all that crap. What would have been new is non-locality and quantization. So you would have focused your attention appropriately on those amazing properties and not gotten distracted by the measurement problem because you would have understood it and it wouldn't have been a mystery. And that's still broken in physics, in my opinion, and it's fixable. Okay, so I probably should, let me see if I have anything else here. I'll skip. I have a whole bunch of stuff here, so you can look at the slides. But and it's really, this stuff is not hard at all. And so, but so this would be, I think, maybe kind of the future of physics more generally, is to have both theory and experiments look at the world this way, because what you're doing is you're comparing models that are running on digital computers to experiments that are being done at the quantum mechanical level. And if you don't have a theory about how this whole thing connects, you will make mistakes, particularly with regard to the nature of measurement. And because quantum gravity is, I mean, what a fascinating subject. And if I wasn't too distracted by other things, I'd love to work on that. So that's sort of now what's going on at Caltech? Not much. So the students are interested in this, but the professors, like, what are they going to do? They're going like, I don't know. I don't know what to do with all this stuff, because theoretical physicists don't know what to do with this, but experimental physicists do know how to do this. And so I think you shouldn't leave theory to the theorist. Okay, that's my screed. I guess we have time for questions.
Okay, thank you, Professor. We are ready for questions. Does anybody? I actually have one.
Okay.
So how do you envision the usage of this theory for designing layered control? So if I understood right, it's what you present for SLS. We can decouple the several layers. You design it once at a time, and you have.
You don't really decouple them quite. That's not quite the right word.
Okay.
So let's think about the software running on my computer right now. We have software, we have an operating system, we have hardware. They're not decoupled. But what we have is we have a characterization of the interaction that makes it much easier to deal with it than if we just had, again, just models of the transistors. So if we just had models of transistors, we could run simulations, but we really wouldn't understand what software was, what the apps were. So you can have a theory that kind of abstracts away the hardware, like a Turing machine. So you say, let's pretend this is a Turing machine. I haven't decoupled my software from the Turing machine, but I've taken advantage of the virtualization to do an abstraction. I should have spent a little more time on that.
Yes.
So it's not decoupling. So if you look at the theories we have of layered architectures, and that paper I pointed to at the beginning, which just appeared last year, is an attempt to summarize how all that works. What's the mathematics of doing the layering, which is going to the right side. And then the left side is just statistical mechanics, basically, which has to be redone in order to make it fit with this framework. But that's not hard.
Yes.
I'm not sure this is making any sense. Sorry, it's kind of going fast.
Yeah, and I just wondered, because we have many layers in our systems. For instance, for orbit feedback, we have fast and slow orbit feedback.
Yep.
This is a,
Yep.
let's say, more obvious. And what kind of rules or laws that you envision we could use to when designing these loops, these control loops? Because now we are just doing not by, let's say, engineering, we just follow
Yes.
some kind of intuition to
Right,
where.
right. Yeah, so let me tell you, because this paper has some of it in it, and let me just maybe I can't find it. What is it? Okay, so sorry. Okay, here. This paper, okay. So this happens to one of the examples it uses is bacteria, but here's the basic idea. When you're given two things to start with in a design. You're given what you want the system as a whole to do, and it might be a whole bunch of different functions that you want it to perform. And you have a big box of hardware. So you have two kinds of constraints. You have constraints on what the system as a whole you want to have it do. And let's not think of it as an optimization problem. Let's just think of it as there's a set of constraints, and if you satisfy those constraints, you have a successful design. You can turn it into an optimization problem, but let's just think about you have constraints on how the system as a whole must work. And in this case, for bacteria, there's constraints on what bacteria have to do in the world in order to be functional. And then you have all this hardware. So you have molecules of all sorts of kinds. You guys got all sorts of, engineering components that you're trying to put together. So what you want to do is you want to say, I have constraints from the top, I have constraints from the bottom. Is there an architecture that can not only satisfy all those constraints, but satisfy them even as the constraints evolve? So even if we get a new constraint, I don't have to redesign the whole system. So the way that happens on our cell phones is we got apps, we got hardware, and those are the constraints. You don't have to have an operating system. But you do have an operating system because you don't want to just have one app run on one hardware. You want to have lots of apps run on lots of hardware. So how does bacteria do it? They have lots of genes, they have lots of metabolites, but they have essentially something like an operating system to connect the two. And what we can prove is that that's optimal. And what is it optimal for? It's not optimal for one application and one hardware. It's optimal for lots of applications, lots of hardware, and you want them to all plug and play. And so the theory that's in this paper is what would help you do the design. Now, what's not in this paper is all this SLS stuff. And the reason was deliberate because SLS is sort of such a hot topic. People have now said, oh, well, SLS is architecture. And we're going, no, there's lots of stuff to architecture that isn't SLS. SLS is how to design, the lower layer control system. I'm not sure this is very helpful, but the idea is that there is this, it's called layering as optimization. So you take and turn your problem into an optimization problem. And then if you use the methods here, it creates a layered architecture that solves the optimal problem without loss of anything. So you don't lose anything by layering, but when you do layer, you get a lot of flexibility that you wouldn't have if you didn't. And that's the idea here. And there's this is just a summary. There's just a ton of papers that cites that lays out all this theory.
Okay,
but it's very much in progress too. It's very much in progress.
Okay. I would have more questions, but I would like to leave to the others to have any questions, comments. Sirish.
Thank you, Professor Doyle. Can you hear me?
Yes.
So I have this question on the interaction between several feedback systems. I'm I'm talking from my present work at the particle accelerator feedback systems point of view. So we have several systems working on at several physical with the physical significance, and several actuators, which, for example, the beam stability, orbit feedback, and we have bunch by bunch feedbacks working on it's the same place all the feedbacks are working, but physically we consider them as separate models, and it's highly impossible. I mean, it's not possible to basically consider the whole thing as a one integrated model and design. So we are separating basically feedback control design, for example, or feedback, low level RF. So do you have any advice or experience on how do you approach, what do you compensate in each feedback independent design about the interaction?
Yeah, so that's okay. Yeah. So again, LIGO did a similar thing. They just designed loop at a time. And all they used from my theory was how to design those single loops, which I don't recommend. But once you had the analysis theory, you could check whether you're making any of the errors that you can make doing loop at a time. So if you can do loop at a time and it looks great and it's a disaster, but you can check that. And so what they did was they did loop at a time and they checked it and it was fine. So they said, we don't need the new theory. Now what happens is if you do that and you check it using robust control analysis tools, like what would be in MATLAB, and there's a design flaw, or there's just a fragility that wasn't apparent from the loop at a time, then if you still want to have sparse controllers like you would design loop at a time, then you need to use this SLS stuff, the stuff I talked about at the end. And what that lets you do is it lets you design locally in small parts, small pieces, yet guarantee that the global behavior will be good. And so you need two things to do that. You need the kind of layering theory that's in this paper, and then you need the system level synthesis, or SLS, that I talked about at the end of my talk. And you need to put those both together. And very few people are doing that right now. So this guy, this co-author at the bottom, Nikolai Motny, is one of the leaders in doing this. Aaron Ames is doing this. He's a professor at Caltech. He's doing this in robotics. But I gave you a list of people who are my former students who are doing this in a variety of settings, but most of it's robotics, artificial intelligence, large language models, not much being done in physics. And there's some physics students at Caltech. Well, the problem is we get physics students who learn all this stuff, and then they don't want to do physics anymore. They want to go do, large language models or AI and robotics because the job market is infinitely better. And so it's been hard to keep people in physics once they learn this stuff. But if you're already starting it as an experimental physicist, this is not hard to learn. This math is not hard to learn. If you go through the heart of robust control and have you ever studied H infinity? I mean, I love the math, but when I look at it, pretend to be an engineer for a minute. It's too much math for what you get out of it, I think. And so, but this isn't. This math is all really easy, and you get a huge amount out. I don't know if that answers your question, but.
Thank you so much. Yeah, thank you so much. That was helpful.
We have a question, more question.
Thank you, Professor. Thank you, Professor. So I read just to check the paper. So they talk about the layered control architecture, LCA. It's covered from bacteria to power system, a huge range, almost everything. So my question is, in reality, these systems are different. So from this model, LCA, So where the domain or system level details kick in and where they are common.
Oh, no, I mean, the details are different. So this is a bad analogy, but one of the things that Newton said was gravity on Earth and gravity in the planets, it's the same gravity. Now, then you could say, yeah, but it's like dropping a ball and circling the sun. Those are completely different. You go, yeah, no, they're completely different, but they have one thing in common. The one thing they have in common is what we're going to call gravity. Okay. So what I'm saying here is bacteria and the internet are completely different. They have one thing in common, and that thing is called architecture. And this has not been a subject until recently. And so what this paper shows you is that indeed, these guys there's too much robotics here. So these guys all are, doing robotics. And the problem is, okay, everybody's doing robotics, so it's natural to have a focus on robotics. But you could say, okay, bacteria and robots are completely different. And the internet, bacteria, the internet, and the power grid, completely different. And your brain, okay? Completely different. And then completely different parts, different roles, everything else. But do they have anything in common? Well, I think up until recently, we would have said, no, there's nothing in common. But you say, wow, but they all obey conservation of energy, right? Yeah, okay. And they all have conservation of matter. And then some combination of matter energy is concerned, right? But then you find out that in fact they have something else in common. And that thing is architecture. And this paper tries to explain what that thing called architecture is. And it's not part of physics. And it's not strictly part of engineering or biology. It transcends them in some sense. And it's a new subject. And currently it's kind of exclusively at Caltech, but we're trying to spread it. And my students are, so I have 13 students in the top 9 world universities. So if you're in those 9 universities, there are students of mine there that, know this better than I do. But that's a good question. Like, what do I mean? I mean, and that's the kind of reviews you get. You get reviews that say there are no new laws in biology that don't come from physics and chemistry. And you just know, here's one. And the theorists go nuts because they say there can't be. And then the experimentalists go, thank God somebody's actually explaining our experiments for the first time. This is the first time anybody's done any theory that actually explains our experiments. And so you want to explain experiments, you got to use this theory, I think. And physics has been able to avoid that. I think biology and engineering can't avoid that. And I think theoretical physics would improve if it took into account what you guys do, what you people do in making your experiments. So sort of a rant, sorry.
Okay. There's one more question here. Oh, great.
Just a question about this sparseness and breaking things into local control. Is that sort of problem dependent, or any comment on how you split stuff up, how things become sparse? Is that done for sort of model reduction, or is it kind of a natural thing that you look for?
Oh, no, that's a good question. And I should have been clear about it, right? You have domain specific reasons for that. So for example, if you're a bacterial cell, right? A lot of your communication is done by diffusion. Now, it turns out diffusion is really fast on nanoscale, but still it's a limit, right? And so what you don't want to have is this system have all-to-all communication, right? You want everything to be local. So you want a protein to catalyze a reaction locally. I mean, kind of obviously, right? But our math hasn't allowed you to do it that way, right? So now we have a math that lets you do things like they're really done, right? So you can theorize about cells, you can theorize about the internet. And so, but the reason you have locality in biology is because you localize a reaction at an enzyme and you control it there as well. So an enzyme and so there's tons of enzymes, but there's delays in communicating between the enzymes. And so the enzymatically catalyzed reactions naturally has a kind of sparsity to the hardware that you can't avoid. Now you might say, oh, I want to make one huge enzyme that does everything, right? Well, you just can't do that. And so what you have is a whole bunch of enzymes that are distributed all over. They have to talk to each other. They have to work together, but they're sparsely connected. They're localized and everything. That's one example. And the power grid, okay. You have distributed generation. You have distributed use, and everything's sparsely connected and everything's very localized. And you can imagine you want some God in the sky that just powers everything, but you don't have that. You have generators and they're distributed and localized. And so everywhere you look, it's like that. And the internet, I mean, it looks like we're all together sitting here. If people are on Zoom, they're all over the world. It looks like we're all kind of in the same place, but we're not. So we create this illusion that we're in the same place. But the systems that do that are sparse and localized and delayed and have all these features. But if you do the design right, you never notice. So if you design a cell right, you don't notice that it's got all this severe constraints on what it's doing. It just works, right? So what we have lacked is a coherent theory, either to reverse engineer biology or forward engineer. And the internet was just a big hack by geniuses, right? But the whole thing's crashed multiple times, and they go, "Oh, okay, we didn't know about that." Okay, and then you go and they come over and say, "Hey, you math guys, can you help us fix this?" And you fix it, and it goes fine till it crashes. Now we just want to stop those crashes, right? You want to do the intelligent design and not just have evolution take its course. And so I'm a believer in intelligent design, not in biology, but in engineering and science. And we need more intelligent design and less hacking. I mean, we live in a world of hacks. And how's that going? Like burn fossil fuels. What could go wrong, right? Let's give cell phones to our 9-year-olds. What could go wrong, right? We got to get better at that. I think we could do theoretical physics infinitely better.
Appreciate it. Thanks. I'm also encouraged that I spent a lot of time in the late 80s trying to read mu synthesis and H infinity papers. I'm glad to hear the new one is going to be easier.
Oh yeah, no, I really apologize for that. I mean, yeah, it was, the main H. I'll just tell you one anecdote. Was this main H infinity paper, this DGKF paper, my most cited paper, I think. My friends, these are my friends, say it's the worst paper in the history of control theory. And of course, their reason was before that paper, if you wanted to write a paper on H infinity, you basically had to have a PhD in pure math, not applied math, pure math, basically. So it was a small club. And then that paper just turned it into two Riccati equations. So it let the riffraff in, right? But there was another reason that's a bad paper. It's just a bad paper. And it's all my fault. It's entirely my fault, right? It's just a bad paper. And so one of the reasons I don't co-author with my students is I just ruin their papers. And so I say, okay, I give them the basic ideas, and then I go, okay, don't talk to me. I'll just ruin it. So no, I really want to apologize for the whole 80s, right? I mean, it was unnecessary. I'm doing a PhD in pure math, and I'm not thinking about I don't know. And then the other thing was the engineers I was working with were so smart. Anything I do, they would figure out, right? So I was really spoiled, and I apologize for my behavior in that regard. I'm trying to be better.
Well, we appreciate it all. Thank you.
Oh, and let me say, be, you know, ask me questions, offline. I have tons of more material. And actually, if anybody on the experimental side decides they want to do theory, I'd love to help. Because you probably know all the theory you need to know, and you just need to learn some new math. I mean, that's it, right? I mean, the stuff you know about the theory that's right isn't going to change. And gravity and quantum mechanics. I mean, the basics there, they're all right, right? It's just the interaction with measurement that's all screwed up. And so I think you guys can fix that.